So today's lecture is all about Lebesgue outer measure. Okay, so measurement of things like measurement of weight, measurement of area, so measurement of height. These are all familiar to us. But mathematically, how we define outer measure? So we are going to define. So when we measure, say, area of some rectangle, so what do? We have a collection of standard units. So suppose if the area of the rectangle is 20 square unit, then we have a collection of standard unit. We keep on comparing with the standard unit. So for example, 25 square unit, then keep on decreasing, 24 square unit, 23 square units, like that. So ultimately it will hit the 20 square unit, and that is the minimum from the collection of the standard unit, that is exactly equal to the area of the rectangle we want to measure, that is 20 square units. So like that, because we are taking the standard unit bigger than the area of the rectangle we wanted to measure, that is why it is called outer measure. So we are taking the bigger unit from the standard unit, collection of standard unit, and we keep on decreasing till it hits exactly equal to the area of the rectangle. That is what we wanted to measure. So that is why it is called outer measure. So we have this collection of standard unit, measuring unit. We want to measure the area of this rectangle. Okay, so then we keep on comparing with the standard collection of standard units. We take the first one, bigger one. So and then second, that is approximation is better than the earlier one. So ultimately we hit the smallest one, that is exactly equal to the area of the rectangle we wanted to measure. Okay, that standard unit will take the area of the rectangle that we wanted to measure. All right, so like that. So suppose for a given epsilon, we subtract area shaded blue, okay, from the standard unit. All right, that is exactly equal to the area of the rectangle. Whatever small it may be, if we subtract something, the resultant will be less than the original area of the rectangle. That is quite familiar to you. Suppose area on the left side is the resultant after subtraction, and then measure of the area on the right side is the original area of the rectangle. So that will be greater than the resultant area after subtraction is met. So equivalently you can write like this: from the measure of the standard unit that is exactly equal to the area of the rectangle you want to measure, you subtract an amount of epsilon. Okay, that resultant area will be less than area of the rectangle. All right, so in another way you can write like this: member of the standard unit that is exactly equal to the area of the rectangle will be less than area of the rectangle plus some epsilon. All right, so then the right hand side is the outer measure of the rectangle, that will be denoted by m star a. Okay, so one member from the collection of standard unit exists for each epsilon such that that is less than area of the rectangle plus epsilon. So for example, let us try to understand this from very familiar situation in our day-to-day balance, buying things, measuring weight or something like that. So we want to measure the weight of this ball, and then we keep on comparing with the standard unit. Okay, so suppose the weight of the ball is 3 kg, then we put 3 kg on the left hand pan of the balance. Okay, that exactly balance is met that. Okay, but after that, if you put a small amount of area on the left hand side, the balance will go down in that direction. That is quite familiar to you. That is what is happening mathematically, what I explained about the epsilon. Okay, so a small amount if you put on the left hand pan, okay, the balance will go down in that direction. Okay, so that is the real world situation happening, and that mathematically we want to translate that things into mathematical equation. Okay, so let us first define an interval. So in measure theory, by an interval we mean an interval of this type, closed on the left side, okay, and then open on the right side. I is equal to AV, and it can be written as like this: x such that x is greater than or equal to a and it is strictly less than b, where a and b are finite. Okay, so in case if a is equal to b, I is said to be an empty interval. So the length of the interval is equal to difference of the endpoint. So length of the interval is denoted by li, that is equal to b minus a. All right, so like this, suppose we have a collection C. The outer measure, Lebesgue outer measure of a set A is given by this formula m star A. It is the symbol for outer measure of a set A and is given by infimum C summation LIN. Okay, where infimum is taken over all cover. So what is cover? Cover is a collection of interval whose union is superset of A. Okay, so union that is equal to n going from 1 to infinity INs are interval. Okay, so C is the collection of cover of the set A, means it consists of cover IN, it consists of cover JN, it consists of cover KN, and so on. So C is all the collection, C is the collection of all cover. Okay, so what do you mean by cover? Cover is collection of interval whose union is a superset of A. Okay, that we call it cover of A, and C is the collection of all possible cover of A. So here the infimum is taken. From that cover you take the length of the constituent interval and sum of, then you will get a real number. So like that, if you take another cover you will get another real number. So you have a collection of real number. From that collection of real number you find the infimum that will give you the outer measure of the set A. Okay, that is all about the definition. So for a given epsilon, just like in analogy with the explanation illustration I saw about the area of the rectangle and the balance, for a given epsilon there exists a cover IN of collection C such that some length of the interval of the cover is less than or equal to m star A plus epsilon. So this is directly coming from the definition of infimum, and that I already explained. Okay, so that means the left hand side is a member of the standard unit, one member of the standard unit. Okay, that will be less than measure of the area plus some additional epsilon. So if you add up something more, that will be greater than. That is the meaning of this one. So just using the definition, okay, let us now try to prove some elementary, very important fundamental theorem that we are going to use in the further theory development. Okay, so theorem number 1. So outer measure is never negative. Okay, outer measure of any set is never negative. And number 2, outer measure of the empty set is equal to 0. All right. Number 3, outer measure of a set A is less than or equal to outer measure of B if A is a subset of B. Alright, so number 4, outer measure of any singleton set X is equal to 0 for any X in R. So let us try to prove these 4 results. They are very elementary but very, very fundamental. We are going to use these things in the the complex theorem. Okay, so number 1, let us prove it. So for any cover IN of A, so cover IN of A means cover IN means it collection of intervals whose union is a superset of A. So out of collection of C is the all possible cover of A, that you take a cover IN from the cover. So the summation summation LIN, the length of the interval in the cover, is a non-negative. Okay, as the length of any interval cannot be negative, so length of an interval cannot be negative, so this is non-negative number. So if you take infimum of non-negative number, the number will never be a negative number. Okay, so that is why the infimum of of a set A, or outer measure of a set A, that is infimum, so it is equal to infimum over the collection C summation LIN is taken over all non-negative number. Therefore outer measure can never be a negative number. At the most it can be 0. Okay, so number 2, let us try to prove result number 2. we know that empty set is a subset of any set. Okay, empty set is a subset of any set, and therefore it is also a subset of the empty interval. So what is empty interval? I is equal to AA. So n points are the same. Okay, so that is empty interval, and empty interval has length 0. So I is a number. I is a member of the collection of all cover of phi by intervals. Okay, so this empty interval I is also a member of the collection of cover of phi. All right, so but its length is 0. Indeed, we are taking infimum of a set of non-negative number in which 0 is a member. So therefore 0 will be the infimum. Okay, so infimum is 0, therefore outer measure of phi is equal to 0. All right, so next let us see. The cover In consists of the interval I1, I2 like that. All right, so and that is a cover of B, means their union is a superset of B, and A is a subset of B. Therefore the cover In of B is also cover of A. So that is quite simple. A is a subset of B. Any cover of B is also cover of A. All right, so C, it is a member of a collection of cover of B. So this C is the cover of B, and that cover also cover A, because A is a subset of B. All right, so this C consists of cover In, cover Jn, cover Kn, and so on. So many members are there. All right, so let us try to find out the cover of A. Okay, cover of A consists of cover of B and some other additional C prime that cover A but doesn't cover B. Okay, so these two union will give you the cover of A. All right, so suppose you have cover C of B, and then for collection of cover C for B, from that C you take one cover In, that will give you a real number after calculating the summation LIN. Okay, you will give a cover will give you a real number, another cover Jn cover will give you another real number. Okay, so from C prime again, you see C prime consists of additional cover of A. So In prime, cover In prime will also give a real number P, cover Jn prime will also give a real number Q. Okay, so like that. Okay, so cover C will give you a set of real number. From that set of real number you are going to take the infimum that will give you the outer measure of the set B. So but in case of cover of collection of cover of A, so it will give you the same real number in cover B, but some other additional also will be added up. Okay, that means the collection is bigger. From that you are going to find the infimum. That infimum will be less than the infimum of this set of real number gives the outer measure of A. Okay, so let us try to illustrate this one. Suppose C is this C consists of three rectangle, the triangle, and the smallest one is obvious. Okay, and then you have C prime, you have the smallest one. So from C you add up some other triangle, the smallest changes. Now the smallest is smaller than the earlier smallest of C. So smallest of C prime will be strictly less than smallest of C. Okay, that is quite obvious. From the original collection of triangle, that is C, if you add up two more triangle, and that the new collection we call it C prime, then you find the smallest one. The new smallest one will be less than the original smallest one. That is, I have illustrated this example with this picture. Next, in another possibility, okay, so this C has the smallest one, this one, and then in the same C we are putting some additional one. So the smallest one will be the same as the original one, because the additional triangles, they are bigger than the smallest one. All right, therefore in this situation the smallest of the C prime is exactly equal to the smallest of the original collection C. So in this situation, smallest of C prime is exactly equal to smallest of the C. In these two illustration, what we conclude is that smallest of the new collection C prime, that is it has more member, additional member, is less than equal to smallest of the original collection C, which has less member. Okay, so that is what we are going to apply here. You have a cover of B, and you have collection of cover of B, you have collection of cover of A. So collection of cover of A consists of collection of cover of B, some other additional cover also. So that bigger, from that bigger you are going to take infimum that will be less than the infimum of B. Alright, so therefore outer measure of A is less than equal to outer measure of B. Alright, so then number 4, let us try to prove number 4. Consider the collection of interval in. In consists of x, comma, x plus 1 upon n. It is a subcollection of any collection of cover covering the singleton set X. So if you think about the collection of cover of the singleton set X, this interval in, they are also member. If you take n is equal to 1, you have x plus 1. If you take n is equal to 2, you have x plus 1 upon 2, like that. So you have this collection as a subcollection of any cover of X, singleton set X. Alright, so we know that length of the interval in is equal to 1 upon n, that is difference of the n point 1 upon n. Also we know that this infimum of this set 1, 1 upon 2, 1 upon 3, 1 upon n, dot dot dot. What is the infimum of this set? The infimum of this set is equal to 0. Alright, therefore you are going to take the infimum of the collection of all cover of X, and that collection in are a member, and this in it has length 1, 1 upon 2, 1 upon 3, like that, and the infimum of this subcollection is equal to 0. Therefore outer measure of the singleton set X is equal to 0. Alright, so next, another very important example. So outer measure is translation invariant. Okay, that is m star A is equal to m star A plus X. So the set A has been translated by an amount X, that is we call it A plus X. So outer measure of A plus X is exactly equal to outer measure of A. So this statement we call it outer measure is translation invariant. Okay, so how we define A plus X? A plus X is equal to Y plus X, such that Y is a member of A. So that is outer measure is translation invariant. Alright, let us try to prove this one. For each epsilon, there exists a collection in, consists of I1, I2 up to I infinity of intervals such that A is a subset of their union, that is the cover. Okay, so according to the definition, m star A greater than summation length of the intervals in minus epsilon. That is, this is coming directly from the definition. Okay, so it is obvious that if union in covers A, then A plus X is a subset of union in plus X. Okay, so therefore for each epsilon we have what we have, m star A plus X, that is less than or equal to summation L in plus X, that is what is the length of the interval L in plus X is equal to length of the interval in, and that will be less than or equal to m star A plus epsilon. Alright, so it follows that m star A plus X is less than or equal to m star A. Let it be inequality number 1. Alright, so it is true that A is equal to A plus X minus X. So if you put A plus X is equal to B and minus X is equal to Y, you can write this equation as B plus Y, where B is equal to A plus X and Y is equal to minus X. So applying result 1 equates inequality 1 to B. So what do we have? B and B plus Y. Outer measure of B plus Y is less than or equal to outer measure of B. Alright, so now let us revert back the substitution, that is B is equal to A plus X and Y is equal to minus X. Then what do you get? Putting back B is equal to A plus X and Y is equal to minus X, we have outer measure of A is less than or equal to outer measure of A plus X. Let it be inequality number 2. Combining 1 and 2, what do we get? The equality m star A plus X is exactly equal to m star A. So